Okay, so today we're going to continue looking at algebra in the Islamic world. I think we've got two more topics to go on. So here's a big one. We're going to have a look at Umar al Kayyami and the cubic equation. Because we've already seen that they could solve quadratic equations. So the next thing would be, well, let's solve the cubic equation. But we know that that's something that can't be, what's happening here? Oh, that can't be done by Euclidean methods. So let's talk about this fellow. He's a Persian, worked in around the year 1100, from around 1075 to around early 12th century. So at this time, what did the world look like? So we know that the Abbasid Empire, the Islamic world, sort of covered, from Samarkand to Morocco. So there was this broad swath of land, but as I've mentioned before, it started to break up. So it was too big. So local rulers would sort of set up their own little fiefdom somewhere, and so the Abbasid world was sort of cut down to basically what's Iraq, Saudi Arabia, Egypt, sort of that area. People came from sort of like Central Asia. So these are the famous barbarians that you've heard about in history. So around this time, the Seljuk Turks sort of came in, and they basically took Iran, and they started working, going into Anatolia, which is Turkey. And the Seljuk Turks is actually why Turkey is Turkish, because they're the Turks that came in that made it so. And so at the time, Anatolia was run by the Byzantine Empire, and so they started cracking that and making that. So the Seljuk Turks sort of had an empire that, for our purposes, had Iran. And so that's where Umar al Kayyami sort of worked. But to the east of the Seljuks were the Karakhanid Khanate. Basically, just think of that as Uzbekistan. In Uzbekistan, there's a city, Samarkand, which is a famous kind of city, a learned city. It's famous for its astronomy there. It had an observatory. And so Al-Kayyami actually went there in I guess like in his 20s to work there. And then he came back to what's Iran, particularly Isfahan, which is another kind of famous learned city. It's in Iran. It's another one that has an observatory, a lot of learning going on. And so what kind of work did he do? So a famous book of his is a commentary on the difficulties concerning the postulates of Euclid's elements. So those of you who've done college geometry, have you seen Sakari? So sometimes you talk about Sakari. Sakari is considered the first person to, he worked in the 1700s, and he kind of wrote this famous book which is called Euclid Without Blemishes, where basically he was trying to work out about the fifth postulate. So the fifth postulate of Euclid was the one about parallel lines don't meet. And this has annoyed mathematicians for ages and ages, because the fact that parallel lines don't meet, they want that to be a theorem and not an axiom. So they were feeling like you should be able to prove that parallel lines don't meet. And of course, the reason why you have to have that as a postulate, an axiom, is that it's possible to have geometry where parallel lines meet. For example, in spherical geometry, what are straight lines in spherical geometry? Well, they're great circles. And any pair of great circles is going to intersect lines of longitude of great circles, and they meet at the North and South Pole. And there's also possible to have situations where you have a line and a point, and there's going to be lots of lines through that which don't meet this line. So there doesn't necessarily have to be a unique parallel line, and that's hyperbolic geometry, which people who did college geometry probably learned about. Anyway, this work was known to Sakari, so this is kind of maybe the first text in that, can be considered the first text in that search towards non-Euclidean geometry, which happened around 1800. So that's a pretty important book. He's very famous for working on the Persian calendar. So that's why he left the Samarkand and went to Isfahan. He was there to work on the Persian calendar. So we all heard of AD, or there's AP, Anno Persi, Persisi, or something like that. So it's the Persian calendar. So we all know that there's a Muslim calendar. And does anyone know anything about the Muslim calendar? It's a lunar calendar. Okay, so lots of things are lunar. For example, when we celebrate Easter, there's it's like a mixture of lunar and solar, right? Because it has to be, what is it, the first Sunday after the first full moon? First full moon. So that's telling you there's some lunar component after the spring equinox. Okay, so the Islamic calendar is a lunar calendar, and that's okay for Arabs because they're a desert people, right? But lunar calendars are kind of bad because you have to keep on changing things. You have to have leap days all the time to keep the lunar calendar in sync with the solar calendar. And the solar calendar is important, right? Because if you do agriculture, you are dependent upon the sun, not the moon. So you're dependent upon, when is the first day of spring, that kind of thing. So the Persian calendar differs from the Islamic calendar. They both start at the same point. So for them, year one is what we would call 622, when Muhammad went from Mecca to Medina. That's the famous Hijra, the famous migration. That's the starting point for the Islamic calendar. It's the starting point for the Persian calendar. But the Persian calendar wanted a solar calendar. And so they actually had the most purest solar calendar that there was. They actually figured out the length of the year to some absurd amount of decimal places. And the Persian calendar was fixed by, they divided the sky into 12 bits. And when the sun entered that part of the zodiac, then that would be the start of the month. And so they never had any need for any leap days or anything like. The Persian calendar months would vary from different year to different year. There could be 30 or 31 days in a month, depending upon where the position of the sun was. So it's not particularly useful calendar in that you have to have like a table to know, oh, you know, this year, this month has 31 days, and oh, next year, this month is going to have 30 days. But it's super precise from solar things. It got to be such a pain that the Persian calendar was actually next updated, I think around the early 19th century, early 20th century, when the Shah of Iran made the Persian calendar. It's still solar, but they had fixed months. So because they didn't like that idea of months varying in time, and that's actually the calendar that's still used in Iran today. Anyway, so that was the work of him. He worked on it for like 6 years or so. He also wrote Algebra, his book on algebra, which we'll be talking about in a little bit. And he also wrote on binomial coefficients and extracting roots. So again, he knew the work of Al-Karaji, and he set about making popular the idea of the Pascal's triangle and using that to how you extract roots. And in fact, in Iran, Pascal's triangle is known as Umar al Kayyami's triangle because he did that. He's also a famous poet, he became very popular in Victorian times when a guy called Edward Fitzgerald translated his verses into English, and he published in 1859 the Rubaiyat of Omar Khayyam, which you might have heard of. So famous lines like, "The moving finger writes and having writ moves on." Has anyone ever heard that? And then the other one is, "A book of verses underneath the bough, a jug of wine, a loaf of bread, and thou." Yeah, so there's Omar Khayyam sitting under a tree with a jug of wine and his sweetie there. So, anyway, he actually got into a bit of trouble because he wasn't considered a very good Muslim, so he sometimes got into trouble. But anyway, we're interested in what he had to say about the cubic equation. Okay, so the motivation for him looking at cubic equation comes from Archimedes. And so Archimedes in The Sphere and the Cylinder, Book 2, Proposition 4, deals with this problem of you have a sphere and you want to cut the sphere such that the ratio of the volumes are m to n. And Archimedes showed that that's equivalent to the problem of taking a line segment and cutting it at a certain point such that this ratio of lengths is the same as this ratio of areas. And so if you cross multiplying, you see that you actually get a nice little cubic equation there, which he then solved. I'm sorry, that solved by intersecting. That's going to kill me. By intersecting a parabola with a hyperbola. Okay, and you can kind of see that if you do this, you can use a parabola. You can solve for y. Put that into there, and you'll get y replaced by something times x squared. So you'll see you get a cubic. And that was his motivation. And he wanted to do the same for all 19 different types of cubics. So remember, okay, for them, it's a different cubic if you have like a different arrangement of positive numbers. So this is the cubic cube plus number equals square, right? And so there's 19 different ways that you can arrange those things together. Okay. And so as I said, there's 19 different ways of doing that. Okay. So he wanted to do everything with geometry, okay, because that's the classical way of doing mathematics. So he writes, this is a quote from Umar: "Whoever thinks algebra is a trick in obtaining unknowns has thought it in vain. No attention should be paid to the fact that algebra and geometry are different in appearance. Algebras are geometric facts which are proved by propositions 5 and 6 of book 2 of Elements." So we've seen that those propositions are the core ways that they prove the results for quadratic equations, right? That you've got some square equals some other square in a rectangle. And you've probably been working on that on the homework for this week. And so when he goes ahead and does things about cubics, he's got to do the same kind of geometric things, but since it's a cubic, that means he's got to do things about solids. So it's going to be cubes and rectangular parallel pipeds, which are kind of like the three-dimensional analog of rectangles. Okay. So he's trying to construct solutions. Okay. And so he has to have lemmas that are all geometric, saying about how you can do things in 3 dimensions. So for example, given a rectangular parallel piped whose base is the square a squared and whose height is c, and given another square b squared, construct on that square a rectangular piped equal to the given solid. Okay, so i.e. you're given a rectangular piped whose volume, right, is a squared times c, and you're going to find h such that b squared times h equals a squared times c. Okay, so to us this is kind of like blindingly obvious, right? Because you just, as arithmetic, right? If you've got a squared times c equals b squared times h, then obviously h equals a squared times c divided by b squared. There's nothing to see here really, but he has to show how you do it using Euclid. Okay, so what you do is you use Euclid to construct a line segment k such that a to b is the same as b to k, and then construct h so that a to k equals h to c. Then the solid whose base is b squared and whose height is h is equal to the given solid, and then he proves that by using proportions, which we kind of hate because we just want to do just normal arithmetic. But if a to b is the same as b to k, then if we square this, then a squared to b squared is, well, we can replace this a to b by b to k, right? The b's cancel, we're left out with a to k, and we've constructed a to k such as a to k is the same as h to c. And so that does that, and so then we've got a squared is to b squared is the same as a to k is to h to c, and then a squared is to b squared is the same as h to c. We then cross multiply and we get our result. And of course, the way that you find those line segments is by using similar triangles. So this is how you use Euclid. Right? These are similar triangles, so A is to B as is C is to D. So given any 3 of them, you can find the 4th by using that geometric construction. So fine, that's the kind of thing he does. So let's actually have a look at an example. So cube and sides equal a number. So this is y cubed plus my equals n. And so he actually gives a procedure, a construction to go ahead and produce that. Okay, so let b be the side of a square equal to the number of roots. So that means b squared equals m. Let h be the height of a rectangular parallelepiped whose base is b squared and whose volume is n. Okay? And you can do that by the previous lemma. Okay. Then you get a parabola whose vertex is b, axis is bz, and parameter b, and place h perpendicular to bz at b. Okay, so here we go. Here's our b, here's our axis. So we're putting our parabola here. B is going to be our parameter. And then we're going to place h here, perpendicular to BZ. Then we put a semicircle on it, on this h, and it's going to bisect the parabola at D, and then we drop our perpendiculars, and then BE is going to be our desired solution to the cubic. Okay. BE cubed plus m times BE equals n. Okay, why is that so? Well, hopefully we've done enough of these that you can see why. It's on its D lies on a parabola, so its ordinate squared equals b times its abscissa. Okay, and so if we let y be the ordinate and x be the abscissa, we've got y squared equals bx. D lies on a circle, so remember the quadrature of the square. The thing that defines a circle then is that this squared is equal this times this. This is something that we've seen earlier on. So that means x squared equals y times h minus y. You eliminate x, and you get this actually degree 4 equation, but we can divide through by y, and that corresponds to this thing that's actually not a solution, that's just an artifact of our method of doing it. And so after we divide through by y, what do we get? Well, hang on, we get y to the 4th on b squared equals hy minus y squared. We're going to divide through by y. And multiply through by b squared, we get y cubed equals h b squared minus b squared y. We bring the y over here, and then that does it for us, I think, because hb squared is n by construction, and b squared is m, again by construction. So it works. Okay. Why must there always be only one positive solution? So can anyone give a reason why this is going to have, there is always going to exist a positive solution and there's only going to be one? Can anyone give an argument? Well, from a start, just from the method of construction, right, we've got a parabola and a semicircle. So no matter how you change m or n, and no matter how you change b, right, you know, the semicircle can get smaller or smaller, or bigger and bigger. The parabola can get wider or narrower, but it's never, we can kind of see that it's never going to cross more than just once. Can anyone give me just a sort of like a calculus answer just based upon looking at an equation here? What can you tell me about y cubed plus my if m is positive? What does calculus tell us?
When y is negative infinity.
Sorry?
So your immediate value term approaches negative infinity as y approaches negative infinity, and also.
It's going from negative infinity to positive infinity, is that what you're saying? Okay. And how does it do that? How does it go from negative infinity to positive infinity? It's continuously, but also, is it monotonic? Is it always increasing? What's its derivative? 3y squared plus m. So y squared is always going to be positive. M is a positive number. So this derivative is always positive. So this is always increasing. N is just a constant value. And so it's going to cross that line. It can cross that line. It is going to cross that line. And it's only going to cross that line once. So by some argument, we can come up with that there has to exist one positive solution. So remember, they're only interested in positive solutions, again, because of this kind of geometric kind of thing. Okay, so he did all 19 cases. So 5 of them turn out to be Euclidean. So that means they can be, what I mean by Euclidean is that really they are linear or quadratic equations in disguise. For example, x cubed equals mx is not that, we can see straight away what the solution is, right? X equals 0 is going to be a solution. And then plus or minus the square root of m is going to be another solution. So we can actually just see the solution. So 5 of them are trivial like that. So there's only 14 that need fancy ways of doing it. So they need conic sections. And he came up with 14 different methods involving some combination of 2 of parabola, hyperbola, and circles. He also discusses the number of solutions that you can get. And remember, we're only talking about positive solutions. And so that can either be 0, 1, 2, or 3. Depending upon which case you're dealing with, where, what the form of the equation is and what the actual parameters are. And so since he's looking at curves intersecting, if there's no zeros if the curves don't intersect. And one way you can get one solution is if the curves just touch tangentially. So those tangential solutions are actually going to be like borderline cases, because if curves touch tangentially, if you change the parameter one way, you're going to get 2 solutions. If you change parameters another way, you're going to get 0 solutions. Okay. So he's doing geometry, but he's doing algebra, and he really believed that he was doing algebra. So he says here, one of the branches of knowledge needed in that division of philosophy known as mathematics is the science of algebra, which aims at the determination of numerical and geometrical unknowns. Algebra, by the help of God and with his precious existence, I say that algebra is a scientific art. The objects with which it deals are absolute numbers and geometrical magnitudes, which, though themselves unknown, are related to things which are known, whereby the determination of the unknown quantities is possible. What one searches for in the algebraic art are the relations that lead from the known to the unknown, to discover which is the object of algebra as stated above. So for him, algebra is just given unknowns, you want to find unknowns, you're given relations, and using those relations, you find what the unknowns are. That's his definition of algebra, and it doesn't matter if you're doing things geometrically or you're doing things arithmetically, it's all algebra. But we do not think that this is a solution. Okay, because what has he found? He has constructed a length. To us, this is not good enough. I mean, a length, what we consider a solution is a number. Okay, so we want a formula like the quadratic formula. And he knew this. He said, and he wanted a number, but he couldn't find it. He said, as for a demonstration of these types, if the object of the problem is an absolute number, neither we nor any of the algebraists have succeeded, except in the case of the first 3 degrees, namely number, thing, and square. It's interesting that he thinks of quadratics as 3 degrees, but anyway. But maybe those after us will. So he's stating that this is a big problem to solve, right? To come up with a formula for the cubic equation. And eventually that did happen. That happened in the 16th century. It's actually one of the highlights of the Italian Renaissance. So it never gets that press. Okay, was the Italians they came up with a formula for the cubic and the quartic, degree 3 and degree 4 equations, by doing purely algebraic methods. And that's where we'll kind of get to by the end of the class. Well, I think some of you is anyone here talking upon that? It's one of the things. Okay. So let's have a further discussion on the number of roots. So let's have a look at this problem. X cubed plus n equals mx squared. Okay. Now, if we look at it, it's kind of funny because he thinks of this as in like a parabola meeting a hyperbola. But when we look at it, we think of it as a cubic meeting a parabola. Okay? Because x cubed plus n, that's something which is kind of monotonic. We know that that's going to we know what x cubed is, n just shifts it vertically, right? So it's going to kind of look like, oops, that's a terrible, it's supposed to be flat there. And mx squared, right, is going to be a parabola, and the m is going to make it narrow or whatever. So we see that straight away that there's going to be a solution here, but that's kind of negative. And we can see that it's possible for it to have 2 solutions, right? Because the x cubed is going to go faster than it's going to eventually beat out the x squared, right? So if it does cross it here, the x cubed is going to cross it over here. So that's going to be 2 solutions. But if n is too big, if we lift this up too much, then the x cubed is always going to go faster than the x squared. And so it's going to be possible for there to be no solutions. And it's going to be possible to be 1 solution if it just touches it tangentially, right there. Okay. And so what Umar did was he looked at it and said, well, maybe let's have a look at the cube root of n. And he kind of looked at the cube root of n because, right, if x is like the cube root of n, then this is like n, this is like n, this is like m times n to the 2/3. So maybe that's going to work. And it does work. Because if the cube root of n is bigger or equal to m, then mx squared, right, has to be bigger than n. Because x cubed plus n equals mx squared, and everything's positive. So mx squared is bigger than n, and mx squared is bigger than x cubed. Right? But n is bigger, if we have this hypothesis, than m times n to the 2/3. And so to have a solution in this case, x would have to be bigger than the cube root of n. But x cubed is less than mx squared, so that means x is less than m. So we've got x here and we've got x here, and that's a contradiction. So that there's no positive solutions. But we can do better, right? If I gave this as a calculus problem, you could actually solve it, right? Because what would we do? How do we go about solving this as a calculus? So first off, we would say fx equals x cubed plus n minus mx squared. Okay. And what we'd find out when this was a minimum, so we take the derivative, we go 3x squared minus 2mx. So that's going to equal 0 when x equals 0 or x equals 2/3 of m. Okay, and it turns out then if we look at the second derivative, 6x minus 2m, that this then is the minimum. You just look at that. And then if we plug that back into here, we get, what do we get? We get 8m cubed over 27 plus n minus 2/3 squared is 4/9. Okay, and if this is positive, right? Because this is the least value of this, and so if this value here is positive, that means it doesn't have a root. Okay, so if we graph this and it kind of looks like that, nowhere is there a root. So then that gives you a relationship between n and m, and so if we do the changes to 12 and 27, then we get n bigger than 4m cubed over 27. As kind of like the sharp definition, right? And so if you look at the cube root of that, that's where you get that thing from. So you can actually do better than what Umar al Kayyami did. But you need calculus. Or do you? You actually don't need calculus. A later, just like a generation later, Sharaf al-Tulsi actually did this. Okay? And he kind of did it without calculus, but if you look at it, you see that what he actually did was calculus, except he didn't know it. Right? So again, he wants to have a look at that. And we want to find the minimum of that when x is positive. So let's say alpha is that. And as we said over here, if when you plug in alpha into that, you get a positive number, then there is no positive solutions. Okay, so we've got x cubed plus n equals mx squared. This is for x greater than 0. So alpha is the actual minimum. And so you subtract one from the other. You get x cubed minus alpha cubed equals m times x squared minus alpha squared. And he divided by x minus alpha. Okay. So if you do that, you get x squared plus alpha squared equals m times x plus alpha. And so then he plugged in the minimum, x equals alpha. You get 3 alpha squared equals m to alpha. So alpha equals 2m on 3. So he found the minimum without doing calculus, just by. But of course, in dividing by x minus alpha, he's sort of doing, he's kind of looking at the limit as x approaches alpha without actually doing that. So he's dividing by this and then plugging in alpha, which is kind of how, if you remember how you do calculus limits, that's kind of how you do it. So he found he actually found the sharp limit by actually, the sharp inequality by actually doing this kind of trick, which is pretty, I think, pretty clever. Okay. I think that's where we'll stop today.